Thank you, Susan. Good. Probably should say good afternoon, everybody. But here's my topic today: is the cars sinkhole detection and mapping using airborne LiDAR. This is a project funded by Tran-SET, and is a team. The team for this project is right here on the list. Myself and Dr. Susan Bogus, Shirley Barros, and also Paul Neville. So a little bit background about this. I just want to clarify that this presentation is a continuation of last year's Tran-SET conference. So last year we presented a conceptual framework for the using airborne LiDAR for sinkhole detection and mapping. And so now we just want to present the practical workflow, how to make this effectively and accurately detect and map the sinkholes. So basically, sinkholes are natural depressions in the Earth's surface. It's almost always prone to karst area. If we based on the sinkhole it appear or not appear, we can classify them as the potential sinkholes and also collapse sinkholes. So potential sinkholes is in the process to collapse, so which is much more difficult to detect. But collapse sinkholes is already exist, so it's relatively easier to detect. But collapse sinkholes could cause substantial damage to transportation infrastructure assets, like roadways or bridges. And also, so therefore, being able to accurately rapidly detect and map sinkhole is critical to transportation infrastructure asset management and for planning purpose. And therefore, transportation management agencies at all levels, like state, federal, regional, or local, or even tribal, dedicate a large amount of time and money to detect and map collapse sinkholes as part of their infrastructure management system programs. So currently, there are a few ways to detect sinkholes. One is but still the primary way for us to detect sinkholes is through area reconnaissance. Basically, we do visual inspection for the collapse sinkholes and also use the instrument for inspecting the potential sinkholes. There another way we can also locate the sinkholes is a review of different kinds of maps, like topographic maps. And for example, the USGS, topographic, 1 to 25,000 scale topographic maps, or we can use the contour maps, and also use some sort of geologic maps. But of course, this type of maps cannot, identify all the collapse sinkholes because they have a scale limitations. They may be able to identify some big sinkholes, but not for the smaller ones. We can also use aerial photos or satellite image for this, like I'm showing here in the image. But the problem is, all this type of photos or image, they are two-dimensional. It's really hard to detect a three-dimensional one. You can interpret or find the sinkholes successfully from the satellite image or aerial photos, but most times it's really challenging because, like I said, it's a three-dimensional feature. And also, the last option now we can use is like using airborne LiDAR. LiDAR stands for light detection and ranging. Is the technology that use light in the form of a pulsed laser to measure distances. When we use this is really a well-established method for collecting accurate XYZ data, basically three-dimensional data, and it will allow us to examine examine the the Earth's surface elevation change accurately and also rapidly. The resulting data from airborne LiDAR or LiDAR collection are presented in the form of point cloud. So go from there, we can process the point cloud to generate different products, which I will be talking in the next slide. But one really unique feature beyond that, LiDAR can be used to collect data day and night, and even in cloudy days. But another really unique feature is that it can filter to the ground through the vegetation canopy. Like I'm showing in the image, you can have first return, second return, third return, and the last return. It can, like I said, it can go through the vegetation canopy gaps and go all the way to the ground. So which is really helpful for sinkhole detection in the sense, because sometimes some of the sinkholes may be kind of like hide by the vegetations or by trees. So this is really unique characteristic. Like I said, when you get LiDAR data, you always in the point cloud format, but we have to process the point cloud to derive some products. The two popular products is one is the DSM, which is the digital surface model. It's not including the not only the background, the background Earth, but it's also including the the features above the ground, like the trees, buildings, all the other structures. But for DEM, or we call it more like a DTM, digital terrain model, is a bare earth model. It's only the bare ground. It doesn't include any features above the ground. So just the two examples showing you what's the difference between DSM and DTM. The reason I want to mention these two products is because we are going to use them for the process of the LiDAR data to basically we process these two products to identify and detect the sinkholes on the ground. So currently, airborne LiDAR already being used for sinkhole detection, but they are only used to they only use a morphology-based feature extraction. For example, they focus on detecting objects that from a distinct shape transition in reference to their surroundings. For example, geometrically, sinkholes, they are oval-shaped concave depression. But using this morphology-based method has some problem, because sinkholes, they have a varying size, shape, and also appearance under different landforms, and they may not even exist in certain contexts. For example, a dry stock pond, like I'm showing in the picture, and the detention pond, they may be false positively detected as a sinkhole. So basically, currently for the airborne LiDAR-based method, we don't have any context feature extraction to detect the sinkholes. So for the continuation of last year's presentation, here's our practical workflow. So basically, we have to process the data to prepare the data for LiDAR sinkhole detection. So here's the 3 steps. We have the LAS files, which is a raw format for the LiDAR point cloud, and then we process them to a LiDAR dataset. And then from there, we create a DEM tiles, and then we call this big step as the data preparation. Then the next step is a preliminary sinkhole detection. So I'm gonna talk this a little bit of detail in the next slides, but basically we have to do a preliminary sinkhole detection, and then we do a final sinkhole detection, and then the output from this will be a map showing where what's the location for the sinkholes. So for preliminary sinkhole detection, the mapping, really the big step we want to use is basically fill all the, because all the DEM, they are like they also have a sinks which is the lowest point of the DEM. So originally, most of the research focused on just detect where is the lowest point, and then they assume that's the sinkhole. But our method is a little bit different. We fill the sinks first, and then use the filled sinks to minus or to deduct or minus the original sinkhole to detect where all the filled sinks. So this is a kind of like a different route to detect where the lowest point or where could be the sinks. So this way we can do a pixel-based feature extraction. Like I said, we fill the DEM first, and then we use the original DEM. Use the filled DEM to minus the original DEM. So when we do this preliminary sinkhole detection and mapping, we're gonna get a map like on the right-hand side. You can see it's really busy because there are a lot of small sinks that are treated or false positively detected as a sinkhole. Which is really busy. So we have to further filter this to get improve the results. The next one we are going to use is called context-based feature extraction. Like I said, sinkhole may not exist in certain contexts. So in order to do this, the first thing we want to use is called object-based image analysis. So it's a little bit different from the pixel-based image analysis. As we all know, each image is composed by individual pixels. So, but for high spatial resolution image or aerial photos, the problem is that, for example, I'm showing the image, is that we have an original RGB image, and when we do pixel-based classification, you get a map like in the middle, because we know that a single tree is a single tree, but in the middle image, you can see that a tree is classified as, some of them are false positively classified as grass, and some of them are trees or shadows. And when we use object-based analysis, we can solve this salt and pepper issues, like which is a single object is composed by different pixels. So we just basically group all the image pixels through segmentation and then delineate the boundary. So, object-based analysis is designed to deal with high spatial resolution images. So it's considered not only spectral information, also which is basically the image pixel values, but also consider spatial information like the shape and the spatial proximity. For example, if we found a pixel that has a value of tree type, more likely all the pixels around it will be kind of like tree pixels. So that's the basic logic behind it for this technology. So when we use OBIA or object-based image analysis, we can group all the pixels that could be sinkholes together. So like I'm showing on the bottom image, that there's quite a few objects that could be the sinkholes, and then when we use OBIA, all the pixels are grouped together and showing as a blue color here. Another context-based image analysis we may think about is we have to further filter these results. We have to further to remove all the false positively detected sinkholes. Like I said, certain sinkholes won't be on certain landforms or land use type. So we can have all kinds of context data. There's no limit how many type of context data you can have, but some typical things we want to consider is the shape and the proximity, which we already considered, and also soil types, infrastructure boundary. Some infrastructure could also be sinkholes. Like for example, a stadium in the shape of it's really similar to a sinkhole. We can remove them. We can also some sort of vegetation types could be also false detected. Land use, land cover type, and also hydrology, because there could be a lot of dams or other infrastructure type could be positively detected as sinkholes. So when we have all the layers, we can further improve the results. And then the last step we're going to do is a traditional morphology-based feature extraction. We consider about the area, width, length, perimeter, depth of the sinkhole, volume, and elongatedness. But at this moment, we only consider area because we only consider a certain or smaller than or larger than a certain size will be considered as a sinkhole. This is consulted by the National Cave and Karst Research Institute. We guess this number. But as I said, this tool can be expanded to consider more parameters like width, length, perimeters, all kinds of things we can consider in the future. So just some preliminary results. Here's our study area near Roswell. On the west is about 90 square kilometers. And some of the findings we found is that the Airborne LiDAR-based sinkhole detection and mapping method can be used to effectively detect the collapsed sinkholes. We get about 81% accuracy, but this is at the group level. We consider all the sinkholes together. But at the individual level, Airborne LiDAR cannot detect, can only detect sinkholes and ground truth. And the LiDAR detects the sinkholes and also the ground truth sinkholes. They do not have statistically similar morphometric measurements, like I'm showing on the bottom picture there, because some of the cyan color is the actual sinkhole, and then the brown color is the detected sinkhole. As you can see that they all kind of like match the locations, but the morphometric measurements is off a little bit. After further investigation, we found out this is limited by the resolution for the LiDAR, because the LiDAR we are using is a quality level 2. It has a vertical accuracy about 1 foot. So with higher vertical accuracy airborne, we believe that they will provide more accurate detection results. We develop a toolbox for the sinkhole extraction, and we make them available in GitHub. Everybody can download and use it. It's a program with Python. It can be compatible with the standard GS software. And also we develop a user guide, how to use the tool. You can watch this on the YouTube channel. Provide the link for you. Actually, this tool has been used by the industry sectors. In the past year or so, we get a request from different consulting firms. They try this tool. They give us good feedback, and we improve the tool. So the tool available now is a version 2.5, which is kind of like the current available version. So we are continually improve the tool, and you can try and also give us feedback. So I would like to thank Tran-SET for funding this project. Also want to thank New Mexico DOT for also supporting this project, especially District 2, Mr. Tim Parker. He supported us a lot for this project, and also want to thank National Cave and Karst Research Institute in Carlsbad, New Mexico. They are a research institute focused on karst sinkhole research. So with that, I think that's my presentation. Susan.
All right, great. Thank you very much. We have time for a quick question, if anyone has any questions.
Hi, this is Surya Congress. I have questions. Great presentation.
Thank you.
So regarding the data collection, can you please go to the slide where you mentioned filled up sinkholes and non-filled up sinkholes?
Sure. Like you mean the collapsed sinkholes and potential sinkholes, or the I guess
representation of filled. Yeah, this one.
Okay.
So I know we do collect a lot of aerial data too. So the challenge itself is to collect the DEMs and LiDAR point cloud. So how are you going to get the first one, the preliminary sinkhole map, where it is not filled up?
So the not filled up one, there's a national program called 3DAP. It's called Three-Dimensional Elevation Program. It's a national program. So each state is collecting quality level 2 data. For example, for New Mexico, we have already collected the LiDAR data for the whole state, and some of the LiDAR products provided by the data collecting company is that a DEM, is also being QA/QC'd. It has to match the quality level 2 data accuracy requirement, like I said, which is vertical is about 1 foot. So so this data is readily available pretty much for all the states, excluding Alaska, state of Alaska, because they're using a different standard. So I think the goal of the 3DAP is by 2023 or 2022, the whole continuous United States will be covered by the 3DAP. But so from there, you already basically have a preliminary sinkhole that's not being filled. So all you need to do is just find that data, get your study area, and then fill the DEM, and then manage the original DEM. So when you fill the DEM, there's a tool in any sort of a GIS operation is called a fill. So basically, like I'm showing in the map, in the image, you are filling the pixels that has a huge depth difference. Did I answer your question?
Yeah, most of it. So only other query was we just need to assume that the original one from the 3DAP is the data corresponding to already failed one. Is that the assumption that we need to assume?
Yes, correct. Yes, correct. I think, when we run the tool, like I said, if it's a certain size, we can definitely, accurately detect them. I think the size is about 50 square meters. So if the size is less than that, more likely their depth is less than a certain size. So we have kind of like a accuracy issues to detect them. So but for general size of sinkholes, using the 3DAP program data, you can have a good percentage accuracy there. So.
Okay, great. So are you also using any aerial, like drone-based LiDAR data collection?
Well, good question. Yes, we are thinking about for the phase 2 of this project we are going to use a drone-based image, using the structure from motion technology, and then build the three-dimensional data. As a part of my research now, we are using aerial photos that we can get about 2 or 3 millimeter spatial resolution image. Or ground sampling distance, we can get about 2 or 3 millimeter image spatial resolution wise, but for the vertical wise, the accuracy is about 1.5 times of the horizontal accuracy. For example, if you have a horizontally, you have 2 millimeter resolution accuracy, and then the vertical is about it's about like 3 millimeter or 4 millimeter. So, with that type of data, I'm pretty sure we can detect all kinds of sinkhole data.
Yeah, especially with 1 feet accuracy with the DEM data, I think getting a couple of centimeters still is good enough with.
Yeah, absolutely. Yes.
Yeah, that's, thank you. Thank you very much for the information.
Sure. Thank you.
Great. Thank you very much. I think with that, we will close out this session. We had some great presentations, and I want to thank everyone for attending. At its peak, I counted 84 participants in this session. So thank you everyone for participating. And I also want to just remind people that the next sessions, the session 3A and session 3B, will start at 1:30 p.m. Mountain Time. So that's an hour and a half from now. So I look forward to seeing everyone in the afternoon sessions, and thank you for attending. Goodbye, everyone.